Welcome back. This episode is going to be one of the most important episodes of this series. Today we are going to talk about model architecture. At the heart of every language model is the model architecture or design. So let's start looking at what is the most dominant architecture in today's language models. That is the transformer architecture, which is based on a special mechanism called the attention mechanism. We're going to talk about that, but before we go into it, let's look at what preceded the transformer architecture. So earlier we had something called as sequence to sequence. So seek to seek is a machine translation and summarization AI model. So seek to seek is kind of a AI model that takes one sequence of information and turns it into another sequence. Think of it like a smart translator. You give it one sentence in English, it learns to produce another sentence in French. The input can be any sequences. It can be text or even something with a sequence of characters or anything, speech. There are two main parts for the sequence to sequence AI model. One is the encoder, which reads the input text like an English sentence, processes each word, and finally turns the entire sentence into a single thought, a context vector. Now this context vector is handed over to the next part of the sequence to sequence model, which is a decoder. The decoder takes the context vector and starts generating the output sequence. For example, the French translation. So it produces one token at a time by referring to the context vector it was handed. So it is generally handed the context vector as a bundle. There is one drawback or main problem with sequence to sequence. That is, it generates output tokens using only the final hidden state of the input. The final hidden state is basically the compressed vector that it is handed down. It's like generating answers about a book from the summary. The solution for this problem was a mechanism called attention. So the decoder can now look back at the encoder's output at every step. Instead of one summary vector, it focuses on the most relevant parts of the input for each output word. So this gave rise to models like the transformer, which are now the backbone of GPT, Gemini, Claude, all of those things. So the transformer architecture was introduced in 2017, but this changed everything. It replaced the bottleneck with the attention mechanism. So this basically allows the model to weigh each input token according to its relevance. Instead of reading text word by word in strict order, the transformers can also process tokens in parallel. So it's identifying relationships across the entire sentence simultaneously. The output is still generated sequentially, but now every word is aware of every previous word, not just the final summary. So the heart of every transformer model is the idea of attention. So let's look at what attention is. The current state of the decoder, what output has been presented so far, is called Q, the vector of the current state. The previous token set and its associated data and relationships is called K. The actual value of the previous token is also called V. Now with this assumption, this the query, the key and the value, the model computes a dot product between the query and key vectors. The higher the score, the greater the influence of that input on the output. It may sound a lot if you have not gone through the mathematical part of it. The attention mechanism basically computes how much attention to give an input token by performing a dot product of the query and key. A high score means the model will use more of that page's content. Because each previous token has a corresponding key and value vector, the longer the sequence, the more key and value vectors need to be computed and stored. So this is one of the reasons why it is so hard to extend context length for a transformer model. So the attention mechanism is almost always multi-headed. So the multi-heads allow the model to attend to different groups of previous tokens simultaneously. So with multi-headed attention, the Q, K, V vectors are split into smaller vectors. For example, in case of Llama 27B, it has 32 heads, meaning the QKV will split into 32 vectors and resulting in 128. The output of all attention heads are then concatenated. An output projection matrix is used to apply another transformation to this concatenated output before it is fed to the next computation step in the model. In a typical transformer architecture, it is composed of multiple transformer blocks. In general, each transformer block contains the attentional module and the MLP, which is the multi-layer perception module. The number of transformer blocks in a transformer model is referred to as the model's number of layers. Then there is also an embedding block, which we'll talk about in a minute. So a transformer, like I said, is composed of multiple blocks. The number of these blocks determines the depth of the model. The deeper the model, the more abstract its understanding becomes, but at the cost of exponentially more computation. The embedding block. So before any processing can begin, words or subwords must be converted into a numerical representation, a process known as embedding. So the embedding block includes a embedding matrix which maps tokens to high dimensional vectors, and a positional embedding matrix which encodes each token's position in the sequence. Together, these embeddings give the model a sense of meaning and order. So the difference between a cat sat on the mat and a mat sat on the cat is different. So other models that paved the way are AlexNet, sequence to sequence, GANs, all of those things. But since the introduction of transformers, their efficiency, scalability, and versatility have been so remarkable that few architectures have managed to surpass them. Yet innovation continues, with researchers exploring new directions such as a mixture of experts model, state space architecture, memory augmented transformers. A lot of things are going on. So building a model is both a science and an art. It begins with the messy, imperfect data, evolves through complex training, and culminates in an architecture that mirrors aspects of human cognition. From crawling the web to calculating attention scores, the process reveals something very profound. We are not just building machines that predict words. We are teaching them to pay attention, to remember, and in their own limited way, to understand. So in many ways, the transformer's attention mirrors our own consciousness. We read a page or listen to a conversation. We too decide what to focus on and what to ignore. Our minds assign weight, not to every word, but to what feels important. So a model learns this mathematically. We learn it experientially. But the pattern is the same. Attention shapes awareness. The more precisely we attend, the more meaningful our perception becomes. Perhaps intelligence, human or artificial, is not about knowing everything, but about knowing what really matters most. So with that, I think we covered the most fundamental aspect of what a language model does today. There is a transformer right inside it. We'll get into the next episode, but at this point you can pause and think through the workings of how we build a model, what are the different concepts we explored. This should give you a good point to pause learning and just review what we have learned. I will also be putting out a downloadable PDF in the description. Feel free to download it and refer to that, so that if it's a new concept to you, that should give you something to remember and review. So see you in the next episode.